Hello, students. Today we'll talk about a very important topic, which is enthalpy changes. This topic is there in both your AS and A levels and IBDP curriculum. So, yeah, it's a really an important topic. So, we'll talk about enthalpy changes and the different types of enthalpy changes that are there, right? So, we'll discuss the definition, different examples, and writing down equations for different types of enthalpy changes. So yeah, before any uh, start, let's talk about, before discussing the different types of enthalpy changes, let's talk about what enthalpy change really is, right? So it is the amount of energy released or absorbed during a reaction. So while any reaction is happening, either the energy is going to get absorbed or it is going to be released, and that is called enthalpy change. Okay, this enthalpy change will be denoting it by delta HR. If it is at standard condition, we'll call it delta HR naught. That is enthalpy change of the reaction at standard condition. Okay, let's understand it in two different ways. Okay, suppose there is a reaction. A gives you B, okay, plus some heat is released. Okay, so A gives you B and some heat is released. For example, the energy of reactant A was 100 kilojoules, and then the energy of reactant B is 80 kilojoules. So where did the 20 kilojoules go? It was released into this atmosphere. It was released into the surrounding, right? So that is your 20 kilojoules. Such a reaction is called exothermic reaction. So heat is going to be released in exothermic reaction, and the energy of product was B and reactant was A, right? Let's make it R and P just to make it look like reactant and product, right? So here what will happen? Energy of product is obviously lesser than energy of reactant. Energy of product is less than energy of reactant, and mathematically delta HR is said to be energy of products minus energy of reactant. So if we find the delta H here, delta H would be EP minus ER, and since EP is less than ER, EP is less than ER, then the delta H would be negative. That is the first thing that we came to know. So if you have an exothermic reaction, delta H, the enthalpy change is going to come as negative. Why negative? Because the enthalpy of product is less than the enthalpy of reactant. Okay. Then the other reaction, the opposite of this, is called the endothermic reactions. Endothermic reactions are like this. The reactant is going to absorb some heat or energy to form the product. Let's say the reactant had 80 kilojoules. It absorbs 20 kilojoules and forms the product with 100 plus 20, which is 100 plus 80, which is, sorry, 80 plus 20, which is 100 kilojoules, right? So the reactant absorbing energy here rather than releasing energy, right? So here we have obviously EP greater than ER, EP greater than ER, and because EP is greater than ER, delta H is equal to EP minus ER, and that would make delta H greater than 0. In endothermic reactions, enthalpy changes are positive. Okay. The enthalpy change is positive. So what happened here? Energy released And what happened here is energy absorbed. Fine. Examples, some of them we can write. There is energy profile diagram that is asked to draw, but that is more of what we do in kinetics. So we'll do that there. Right now, we are purely focusing on calculation part, which is enthalpy changes. So example of exothermic reactions are combustion, where we heat anything in excess of air, in presence of air. Then you got all formation slash combination reactions. These are your exothermic reactions. Neutralization reactions are exothermic. Neutralization is when an acid is reacting with a base. That reaction is also exothermic. All formation or combination, that means where two reactants are joining together to form a single product, that thing is also exothermic. Okay. There's one reaction N2 plus O2 when they react. That's not exothermic. Otherwise, almost all of those formation or combination reactions are exothermic. And on the endothermic side, we have the decomposition reactions. The decomposition reactions are the reactions where a reactant gets broken down into multiple products. For example, calcium carbonate, when we heat it, breaks down into CaO plus CO2. So this is a single reactant getting broken down into multiple products, right? So we have the examples of exothermic reactions, endothermic reactions, enthalpy change definitions, what really happens in both type of reactions, right? So this is the definition of enthalpy change. Now, once you understand what really an enthalpy change is, the next thing that we need to understand or know is the different types of enthalpy changes. Okay, so without a delay, let's start the thing, which is different types of enthalpy changes. We'll be doing types of enthalpy changes. So first one is enthalpy change of formation. Now you have to be very careful about these definitions because these definitions and the way we write the equations are very useful, or you can say they will be used a lot in solving those past year questions. Okay. So enthalpy of formation, what it is? It is the enthalpy change when 1 mole of a compound is formed from its constituent elements. So we have to form that compound or substance from its constituent elements at standard state. At standard state. Standard state should be there. What is standard state? Standard state is your atmospheric pressure, room temperature, like the pretty standard conditions. Like we are not increasing temperature or pressure, something. Normal conditions that you have around you are your standard condition. Okay. So enthalpy change of formation, how do we write it? So let's say we have to write the enthalpy change of formation denoted by delta HF naught of CH4. Okay. So we have to form 1 mole of a compound. So 1 mole of a compound has to be formed. So CH4, 1 mole of compound is formed. Arrow. And we can't change it to 2 or 3. No, no, no. It's 1 only, right? All the time it should be just 1 CH4 if you are writing the equation. What are the constituent elements? The constituent elements are carbon and hydrogen. So carbon plus hydrogen is H2. Now, how do we know carbon is hydrogen is H2 and not H? That is how hydrogen exists at standard condition. At standard condition, the hydrogen is there in the form of H2 gas. And that's why it is written as H2 gas. And at standard condition, carbon is there in solid form. And that is your equation. But then the question arises, how do we know what is the standard forms of these elements. How do we know what to write on the reactant side? We know we have to write 1 mole of product on the product side, but what do we write on the reactant side? We need to know the standard state of different elements, right? So I'm going to write it down, the standard states for different elements, fine. So for example, H2 we just saw is a gas. Nitrogen is N2 gas. Oxygen is O2 gas. Okay. Three simple ones. Fluorine is F2 gas. Fluorine is Cl2 gas. Then bromine is a liquid. Iodine is I2 solid. Okay. Then you get to carbon, which is a solid. And this carbon is graphite. Phosphorus is P solid or P4 solid. Both are fine. We can use P solid or P4 solid. Both are accepted in the marking scheme. S is sulfur solid or S8 solid. Then all the metals are solid except for one metal which is liquid, and that's mercury. Okay. So these you have to remember. The question is going to be from these elements only. Fine. Let's try to write one down. For example, we have to write delta HF naught, the equation of enthalpy change of formation of bromine. So that would be not bromine. Bromine is like standard only. Let's do HBr. So HBr means we need hydrogen and bromine. So it's going to be H2 and Br2. So it would become half H2 plus half Br2 gives you HBr. Why we did half H2 and half Br2? Because product side has to be 1 mole. And the product side has to be 1 mole, then we have to balance it on the reactant side. We can't do anything on the product side. And that's why we're doing that way. Similarly, another one, we can do delta HF naught of, let's say, C2H5OH. So 1 mole of C2H5OH we will write. And then we have to balance it. So we need carbon solid. So 2 carbon solid. Here it should have been gas and liquid if you forgot. Right? The physical states are important to write. 2 carbon solid, there are 6 hydrogens. So 3 H2 gas, and there is 1 oxygen. So half O2 gas, and that makes it the enthalpy change of formation of ethanol. And you see, it's super simple. Just 1 mole, 1 mole, and 1 mole of product we have to form from the element in the standard state. Okay. Now we are going to move on to the second type of enthalpy change, which is the enthalpy change of combustion. So enthalpy change of combustion, the definition is the enthalpy change when, again, 1 mole of a compound undergoes complete combustion, okay, at standard state or at standard conditions. So conditions are still standard and the compound is undergoing complete combustion in excess air, and obviously it's going to form CO2 and water. So let's see. Suppose we are adding delta HF naught of carbon. So we have to make carbon react with O2. 1 mole of carbon react with O2. That was the definition says to form CO2. If carbon is there, all the carbon will form CO2. That's it. Complete combustion. If you have to write for H2, it will become 1 H2 and all the hydrogen forms water, right? So H2, and when you balance it becomes half O2. If you have any hydrocarbon, so CH4, 1 CH4 plus O2, all the carbon becomes CO2 and all the hydrogen becomes water, and then you balance it. So 4 hydrogens, 4 oxygens, and that's it. Simplest. Some tough ones can be like ethanol to do. It's not tough, it is just the balancing which the students miss. So C2H5OH plus O2 gives you CO2 plus H2O. Now let's balance it. We have 2 carbons, 6 hydrogens, 6 hydrogens, 3H2, 6 hydrogens. And then look at here, 4 plus 3, 7 oxygens. 4 plus 3, 7 oxygens, right? So here we have to make 7 on the left side. 1 is already here, 6 more, so 3O2. That's it. We always do the combustion of 1 mole of whatever compound we are trying to write it for, and always form CO2 and water. All the carbon gets converted to CO2, all the hydrogen gets converted to water. Okay, fine. Then number three is going to be enthalpy change of neutralization. Enthalpy change of neutralization, and it is the enthalpy change when 1 mole of a 1 mole of water, not 1 mole of a compound, 1 mole of water is formed by the reaction of an acid with base at standard conditions. So whenever you make an acid react with a base, you have to always form 1 mole of water. Okay, we have to always form 1 mole of water. For example, if you make NaOH react with HCl, it will form NaCl plus water. Balanced equation. So this will be the enthalpy change of neutralization for this reaction. Okay. But if you have NaOH plus H2SO4, it will form Na2SO4 plus water, and when you balance it will give you 2 water. So this equation is not applicable. We have to form 1 mole of water, right? So then the equation would be half H2SO4, or you can say NaOH, just half it plus half H2SO4 gives you half Na2SO4 plus water. And that is the correct equation for enthalpy change of formation. So that is what we have to take care of. While writing the equation, it should always and always be 1 mole of water. Fine. One important information is whenever 1 mole of H plus ion combines with 1 mole of OH minus ions, the enthalpy changes, the delta neutralization is negative 57 kilojoules. Very important information. When 1 mole of H plus ions join with 1 mole of OH minus ions to form 1 mole of water, 57 kilojoules of energy is released. Okay. So in both of these reactions, because 1 mole of water is formed, it will be releasing 57 kilojoules of energy. Okay. So right now we are focusing on learning how to write down these equations. Once we know, or once we are able to write down these equations, enthalpy change of formation, combustion, neutralization, then we can use these equations to solve those questions which we are going to solve in the next videos that I upload. Okay. So number 4 is another enthalpy change which will be useful in this chapter, and that is enthalpy change of atomization. Okay, so enthalpy change of atomization is the enthalpy change when 1 mole of a compound, not compound, like um, 1 mole of a gaseous atom, we should not call it a compound. 1 mole of a gaseous atom is formed from its element in standard state. Okay. So the element is going to be in standard state, and we are going to form 1 mole of the gaseous atom of that element. Okay. Let's see how it works. Suppose we have to write the delta H atomization of Na. So we'll have to form 1 mole of Na gas. That is what the definition is, right? So that will be Na gas, 1 mole of it. Okay. And what do we form it from? From its own element in standard state. So that is sodium. Sodium in standard state is going to be a solid because all the metals are solids, right? So the equation would become Na solid gives you Na gas. If we have to write down the delta H atomization of, let's say, chlorine, so we'll have to form chlorine here. And what is chlorine in standard state? It is Cl2. So the equation would be Cl2 going to Cl gas or half Cl2 going to Cl gas after balancing. Okay. That is delta H atomization of chlorine. What we are doing here, we are taking a chlorine molecule. This is important. Pay attention. This is 2 chlorine molecules being broken down to form 2 chlorine, right? But if you have half Cl2, it gives you 1 chlorine, right? So this can also be said to be what? Half times the bond energy of chlorine-chlorine bond. So if you break 1 chlorine-chlorine bond, you get 2 chlorine atoms. So if you provide half of that energy, you get, like, instead of 2 mole of chlorine, we get 1 mole of fluorine. Fine. So sometimes these atomization things can be used as a substitute for bond energies as well. Okay. But yeah, right now our focus is on learning atomization. Focus on that. But yeah, always remember bond energies can be related to atomization in questions. Okay. Sometimes in place of atomization, they will give you bond energy. So you can very wisely use bond energies as a substitute for atomization and vice versa. Okay. Suppose you have to write atomization of bromine, okay, or even oxygen. Let's write oxygen. So that's more common. That would be half O2 gas gives you O gas. Okay. So in atomization, we always have to form 1 mole of gaseous atom of this particular element. Fine. Number fifth type of enthalpy change is called ionization energy. Now, this is something you have already learned in your periodicity chapter, if you have done those chapters generally. But yeah, it is the amount of energy required to remove an electron from each atom in 1 mole of gaseous atoms. Okay. So we have 1 mole of gaseous atom, and obviously at standard state, we have 1 mole of gaseous atom, and in each atom from those 1 mole of gaseous atom, we are removing a single electron. That is ionization energy. For example, we have aluminum gas. We remove an electron, it becomes Al plus gas, an electron. This thing is called IE1, first ionization energy. Okay. If you remove the second one from it, it will form 2 positive and it will become IE2, second ionization energy. And then Al2 plus gas to Al3 plus gas plus electron, it will be called third ionization energy. Right? So you just have to remove one electron from each atom in 1 mole of gaseous atoms. Number 6. There is more to ionization energy, graphs and all is there, but that's a different chapter. We are using this in ionization energy as an enthalpy change in our calculation. So that much information is enough for the calculation you're about to do. Okay. Then comes the last enthalpy change, and which is called enthalpy change, or we can just write electron affinity. That is a more common word. Electron affinity. So electron affinity, what is it? So electron affinity is the opposite of ionization energy, right? It is the amount of energy released when one electron is added to each atom in 1 mole of gaseous atoms. So 1 mole of gaseous atom to form gaseous ions, obviously. Here also you can write to form gaseous ions because we are ultimately forming these gaseous ions, right? And here also we can write to form gaseous ions. Okay, definitions are important. That's why I'm focusing on them again and again. So suppose we have, let's say, nitrogen. Okay, so nitrogen gas, you add an electron, it becomes N minus gas. This is called EA1, first electron affinity. Then N minus gas, you add another electron. Slightly difficult it would be endothermic. Energy will be required. That will be called EA2. Overall, it would be energy released only, but yeah, it gets difficult to add more and more electron because you're adding it to something which is already negatively charged. So it gets difficult to add more and more electrons. This is called EA3, third electron affinity, which is going to be even more difficult to add. Okay, fine. So these are the 6 enthalpy changes which you have to know if you want to really solve those Hess's cycle, those Born-Haber cycle, those calorimetry questions very easily. These are used again and again in those, and will need to be very much comfortable with these sort of equations that you have to write in these. Fine. So obviously in the next video, we are going to be solving one of those type of question. Either we'll be doing Hess cycle or Born-Haber cycle or calorimetry. Okay, we'll go that in order. But to solve this, you will be needed to know these enthalpy changes definitions and how to write these equations. Okay, because if you know them, then your time will save. You'll be able to focus more on the questions, solve the questions, and get those correct answers in the exam. Right. So that is what I want from you. Keep practicing, solve the questions, and revise this if you want to solve the if you want to do the upcoming topics related to enthalpy changes. Fine. So yeah, this is it from my side for this on this video. I'll meet you in the next one, and bye bye.